Thank you for watching my presentation on the distribution and origin of hydrogen sulfide gas in the Montney unconventional play in Canada. This is collaborative work between myself at the University of Sunshine Coast and the University of British Columbia. H2S gas is a highly toxic gas. Even at low concentrations, it can be fatal. It's a highly corrosive gas as well. This example here on the right is a pipe that was not specifically designed to hold H2S gas in it and has been corroded quite extensively. Companies need to understand the risk of souring in their area and procure sour service pipe to make it more affordable to evacuate sour gas. The generation of hydrogen sulfide gas is a thermochemical sulfate reduction process or an abiotic reaction. In this particular case, we see that bacterial sulfate reduction can occur as well. However, here we're at greater depths, over 90 degrees Celsius, and bacteria does not survive. So the sources of sulfur include evaporites like anhydrite, gypsum, barite, as well as oxidation of pyrite, sulfur from organic matter, as well as sulfate from fresh water during fracking operations. The hydrocarbons are oxidized as the sulfate is reduced to form H2S, as shown by this equation down the bottom here. So as more Montney formation wells are being drilled, we're starting to see more and more sour gas being discovered in areas that were assumed to be sweet, and this distribution can be inexplicable. You can see in these multi-well pads on this diagram on the side here that we see that there's sour and sweet wells that can be on neighboring laterals. So the reasons why this is happening is not clear. So we're using sulfur isotopic analysis to try to identify the sources of the sulfur. Is it from the neighboring Triassic strata, or is it coming from deeper below in the Devonian? So this model will also help producers to understand the risks in their area of souring and during their well planning procedures. So looking at the sources of sulfate for the Montney, both from the literature as well from our study, we've identified least probable sources and the most probable source. Least probable sources include the organic sulfur in kerogen. The kerogen in the Montney formation is sulfur poor. Oxidation of pyrite would need a lot of oxygen being brought into the system, maybe through frack water. This would be self-limiting, so we'd see a spike of H2S gas generation, then a decline to zero. Sulfate within freshwater during frack water operations would be self-limiting as well. We'd see a spike of H2S generation, then a decline to zero as well. These wells that we're looking at do not decline. They keep a constant concentration of H2S production. So the most probable source of sulfur is probably sulfate. Evaporites like anhydrite and gypsum are seen throughout the Montney. This is an example here in a fracture. I'm also seeing it within some of my core, but it's actually within disseminated throughout. There's also a high percentage of anhydrite in the Charlie Lake Formation. That's a Triassic formation that sits above the Montney, as well as in Devonian rocks below, like the Muskeg Formation. And as I mentioned, anhydrite has formed in the Montney, and we're going to confirm how that is, if it's syn-depositional or post-depositional. This diagram is showing the stratigraphic sections through the Western Canadian Sedimentary Basin where my study is being held. And you can see here the Montney. It's actually sandwiched between sour pools above, like the Charlie Lake, and halfway, and then also below through some Mississippian and all the way through down into the Devonian limestones here. This study is looking at the upper, the middle, and the lower Montney sections. In this case, we've broken it down on the map here. You can see the distributions of where it's sour in the stratigraphy. throughout British Columbia and Alberta. This follows this 120-degree line here of longitude. Here's where we are on the western side of Canada. You can see there's quite a lot of sour gas in the Montney occurring in the Alberta side. This has been developed for quite some time before it was deemed an unconventional system. Over here is the newer parts of the development. These blue areas are Montney producers. So where there isn't any squares, circles or triangles are areas that are sweet. So we can see there are scatterings of sour, and then we can actually get areas where we start to concentrate in areas. Here we have the distribution of the anhydrite stratigraphically in both a table form and in a graphical form. We can see in this example the Charlie Lake has high anhydrite, and you can see there is small traces in the Montney. Again, you can see in this example up to 1% is in the Montney formation. This is confirmed through chemical separation means. I have pulled out anhydrite from these particular samples here, so it does actually exist. This is also seen from Sharma and 69 in this well up in the top here, that anhydrite is actually being found in the halfway, which sits below the Charlie Lake, and this is due to circulation of groundwater as a post-depositional feature. So this could be occurring in the Montney. So SEM textural analysis will confirm whether the anhydrite is syn-depositional or post-depositional. So I have an example here of the oxygen isotopes plotted on the x-axis and the sulfur isotopes on the y-axis. In this green box, these data points are showing the Triassic sulfate composition, and you can see that the sulfur isotope is much lighter than the Devonian sulfate sources that have been sampled in the past. You compare that to the sulfur coming from the H2S gas from the Montney wells, you can see the sulfur has a similar signature to the Triassic sulfate. While you look at the Devonian H2S sulfur, and it has a heavier isotopic signature similar to the Devonian sulfate sources. So this data is starting to show that there is a clear separation between Devonian sources and Triassic sources. Some of the Montney wells are showing a slightly heavier signature, and this could be due to a mixing between Devonian and Triassic sulfate sources. Here's a preliminary model for the H2S formation. I have the mineral sulfur being converted to H2S gas in situ. This is probably not the way it's actually occurring, or you'd expect it to be more continuous in terms of being sour across the area. This is probably what I'm thinking is happening. We have the Charlie Lake sulfur as an anhydrite coming down through a fault system early on, and then as hydrocarbons form, it develops H2S with the anhydrite in the area. This shows the signature of the Charlie Lake and the Montney are similar. In some cases, I mentioned, we have some higher isotopic signatures, and this is probably more of what we're seeing. The H2S gas or the sulfur is coming up through a fault system in the Devonian and mixing with the Triassic source like the Triassic, and this is giving that heavier signature. So this project is showing that the sulfate minerals that are responsible for H2S gas in the Montney are being sourced in the Triassic, or a mixture of Devonian and Triassic sulfate source, and not purely from a Devonian source as some operators believe. We recommend mapping H2S pools above and below the Montney formation, as well as use seismic data to identify any structure across the area. I think this can also be applied to other basins around the world where we're starting to see sourings beginning to occur in places that were assumed to be sweet. Additional work will include sulfur isotopic analysis of other minerals like pyrite as well as organic matter, and then do some textural analysis to determine syn-depositional, post-depositional features for the anhydrite in the Montney. Thank you.